Hey, welcome back to our next video. We're going to continue right where we left off with in finding the eigenvalues and eigenvectors of a 2 by 2 matrix. In this video, we're going to discuss the general solution to the homogeneous system. And in this case, we're going to make use of the exact values we found in the previous video. But first, we'll quickly discuss two theorems that help us with determining the general solution, as well as kind of verifying that it does work for us. So the first theorem we have here is the principle of superposition, and it states that if the vector functions x1 and x2 are solutions of the system x prime is equal to ax, then the linear combination c1 x1 plus c2 x2 is also a solution for any constants c1 and c2. What we want to notice is that in this specific theorem, it doesn't guarantee or state that your two solutions must be linearly independent. In the next theorem below, it will state that, and it will show that whenever you do have linearly independent solutions, any other solution to that system will be a linear combination. So the second theorem states that if the vector functions x1 all the way to xn are linearly independent solutions of the system, for each point on or in the interval alpha to beta, then each solution x is equal to xt of the system can be expressed as a linear combination right over here in exactly one way. So that basically guarantees that. So we're going to continue with the exact same matrix we started with in the last video. And we found that the eigenvalues and eigenvectors were right here as follows. And basing off of these two theorems right over here, it's pretty clear that we're basically just going to write these as, again, a linear combination of the solution, which is, again, of the form y is equal to e to the rt. But again, we need to multiply it by the vector simply because that gives us our system solution. So in this case here, we have that our y, or let's use x, so sorry, x sub h, again, standing for the homogeneous solution. So it's c1 times our vector for the first one, so 1, negative 4, times e to the negative 3t, plus c2, times 1, 1, e to the 2t. So again, by the theorem up here, again, because we were able to find these as eigenvalues, they're already guaranteed to be linearly independent. Given that, we know that we have two linearly independent solutions, meaning in our specific case, for our 2 by 2 case, any other solution will be a linear combination of these two functions over here by this exact theorem. And again, you can easily verify this by simply plugging this back into this equation and verifying the equality. You can just take the derivative of each of the vectored valued functions, as well as the matrix itself, do the multiplication. You can verify that. But again, this is kind of one of the other steps towards finding the solution to the non-homogeneous. And again, remember that whenever we're finding the solution to the non-homogeneous system, we always need to find the solution to the homogeneous first. This is very, very important, not only just for the systems of differential equations, but quite literally for any non-homogeneous case, whether it just be like a linear equation, second order, third order, higher order, etc. You always need to find the homogeneous case because that's usually where you'll have the different methods you're using, like undetermined coefficients, for example. You need the general solution first for the homogeneous before you're able to proceed with, again, undetermined coefficients or variation of parameters. So yeah, again, very quick video. We'll end it here. And then in the next video, we'll go over how to find the solution to the homogeneous or find a particular solution, which again, we'll use towards in conjunction with the homogeneous solution to find a general solution to the particular or the non-homogeneous case. Thank you.